We're now going to talk about graphing solutions to systems of linear differential equations. And here's where we need to be clear about dependent versus independent variables. We're going to have the horizontal axis be for t, because that is our independent variable. And as usual, we will have the vertical axis be for our dependent variable, x. Let's get some values in here. I'm going to make what I usually call an XY table, but in this case, we'd have to call a TX table. So T and X1. If I put a 0 in for T, so I'm going to use 0 and 1 for T. If I put a 0 in for T, X1, well, that's 2 times e to the T. And e to the 0 is 1, so I have 2 times 1, which is 2. And thank goodness that's right, because remember our initial condition for x1 is it has to be 2. What do we get when t is 1? That's 2 times e to the first power. E is approximately 2.7. So what's that going to give us? 5.4, approximately. What about for x2? Again, I'm going to use 0 and 1 just to get a couple of points. X2 should come out to be 4, because that's our initial condition. And yep, if we plug in 0 for t, I get 4 for x2. And then if t is 1, I have 4 e to the 2 times 1. So that's 4 times e squared. And I definitely need a calculator for that. And I get approximately 29.5. I'm just going to call that 30, because I can't graph any more closely than that anyway. So let's see. If I have I'm going to put 1 there on our t-axis. And I need my vertical axis to go up to 30. So let's see. I'm going to mark the vertical axis. Oh, I think units of 5 should do the trick. And I need 6 of those, right? So okay, so these are 5, 10, 15, 20, 25, and 30. Notice our x's are both exponential curves, so I know the basic shape of them. So for x1, it starts at 2, which is about there. And then at 1, it's at about 5.5. So about there. And drawing that in an exponential shape, I'll have something like that. And then for x2, that starts at 4, which is about there. And at 1, it's up at 30. Again, it's an exponential curve, so it's going to have this typical exponential shape. Okay, so this is x1 of t, which is 2e to the t, and the steeper one is x2 of t, which is 4e to the 2t. Now, although x1 and x2 do not depend on each other, right, they each depend on t, they are related. This can be hard to see, but I chose this example to be one where we could see pretty easily what the relationship between the two variables is. So notice that x2 That's our 4e to the 2t. Notice we could get that by taking 2e to the t and squaring it, right? Because if I did that, I'd have 2 squared e to the t squared. 2 squared is, of course, 4, and our rules for exponents tell us if I have a power raised to a power, I multiply the powers. And the reason I'm pointing that out is that the thing in the parentheses here being squared, that's exactly the same thing as x1. In other words, x2 is x1 squared. We can certainly graph the relationship between x1 and x2. And what's strange about this graph is that although the vertical axis has a dependent variable, as usual, in this case, the horizontal axis is also a dependent variable, right? They both depend on t, and the independent variable t does not appear. So what's this graph going to look like? Well, let's see. I'm going to go up to 30 again. And on the x1 axis, I'm going to go over to about, let's say, 5. Now this is the standard x squared parabola. So at 1, 1 squared is 1. If x1 was 2, that squared is 4. Let's see, if x2 was 3, the corresponding if x1 was 3, the corresponding x2 value would be 9. Then we have 4, 16, and 5, 25. By the way, this kind of graph where you have the two dependent variables for your system is called a phase plane. That's why this topic is called phase plane analysis. So this is what we're going to be analyzing, is this type of graph. Now the only way we can get the t in here to get some indication of what's going on is to label dots. So the dot at 2, 4, that's when t equals 0. Remember, that was our initial condition. When t is 0, x1 is 2, and x2 is 4. This is the point 2, 4. And then we also had, when t was 1, we had the point, so this was when t was 1, we determined, maybe I should scroll up and just remind us of that. When t was 1, we determined that x2 was 30 and x1 was about 5.5. So on our phase plane, where we have the point roughly 5.5, 30, that's when t equals 1. And one thing that is nice about figuring out where a couple of t points are is this tells you what direction you would be moving along this curve as time passes on.